annual Taiwan string workshop this year, and today is particularly lovely November. It's unusually hot. So, few announcements before we start our exciting series of lecture. First thing is that for those people who sign up for the dinner tonight and who haven't paid, please do so around lunchtime to the lady outside. And also the Wi-Fi password is over there, and there are those Wi-Fis, so you can connect it. And my name is Henry Chen, one of the organizers, and Yutian and I will be, you should probably get an email from us already about the contact. So please, if anything you need, any local information, or you have any troubles, and please give us a call while you are here. And otherwise, please, feel free, especially for a student asking a lot of questions, because I think we really have an exciting set of speakers for our workshop this time, and I think for the local junior researcher, this will be an excellent opportunity to, get some new idea and mingle with researcher from the other country. So, so I think without further ado, let's get started. And we are welcoming Tatsuma Nishioka from University of Tokyo. And his talk title today will be, are you going to tell us?
I'm going to talk about entanglement entropy and the RG flows and the supersymmetry.
Okay, so let's welcome Tatsuma.
Okay, thank you. I'd like to thank the organizers for giving me this opportunity, and I'm very happy to be here because this is my second time to visit Taiwan, and Taiwan is one of my favorite places to visit. So let me start with my talk, with my introduction. So, can you read this? Too small? Okay. Okay. So yeah, I'm gonna talk about the entanglement entropy. So recently, entanglement entropy appears in various contexts. So this is a quantity defined in the context of quantum information, for example. Oh, okay. Okay, so entanglement entropy is studied in the context of quantum information, originally. And quantum information theory mathematically gives us inequalities, various inequalities for the entanglement entropies and their cousins. And so such inequalities appears to be very mathematical, but it turns out that this is very important to study the quantum field theory. And I'm going to talk about it in my second talk. And in quantum field theory, entanglement entropy is very nice order parameter. And also, so we sometimes study the entanglement entropy by using classical gravity theory. Thanks to the formula discovered by Ryu and Takayanagi. So here we have a holographic formula. And of course, quantum field theory and gravity is related by the ADC correspondence. So entanglement entropy appears in various contexts. And also, so after using the entanglement entropy, we found that some relation between quantum information and also gravity theory. So it is sometimes called a tensor network presentation of the entanglement entropy. And also, so yeah, but basically I'm interested in the studying entanglement entropy in quantum field theory today. Yes? Another?
Yeah.
Oh yeah, okay. Sorry. So so one of the interesting properties of quantum field theory is the renormalization group flow. So I will write it as an RG flow. RG flow here. And to study the RG flow in quantum field theory, we sometimes want to define some function which quantifies the degrees of freedom. It is called C function. And so these inequalities provide us some monotonicity of C function, so which is a kind of requirement that so that the C function measures the degrees of freedom in quantum field theories under renormalization group flows. And I'm going to talk about this part today, and also in my second part. So okay.
Excuse me, you talk about quantum info. It is in which dimension?
Which dimension? Any dimensions.
Any dimension.
Yes.
What about gravity?
Gravity is also in any dimension, but one dimension higher than the dimension
And
of
always
quantum field.
anti-digital gravity.
Yes, yeah, any safety correspondence. So yeah, I'm gonna yes, yeah. But I'm not going to talk about the holographic picture today. Yeah, I focus on quantum field theory side. So in quantum field theories, the entanglement entropy can be defined for any quantum field theory. In any dimensions. So it is a very universal quantity which you can define. So usually, usually, if you want to use the two-point functions, you have to specify your operators you use. So it depends on your theory. So, but the entanglement entropy can be defined for any theories and without any specifying any operators. So this is very universal. And also it captures not only local information but also global properties. So and also, since it captures global properties of quantum field theory, it can be all the parameters for phase transitions, such as confinement, deconfinement phase transition in QCD, and also quantum phase transitions in the context of condensed matter physics.
So you say any quantum field theory in any dimension, but the theory, the QFT has to be renormalizable.
Yes, I always consider the renormalizable quantum
It's
field
quite
theory.
limited. It is very limited in higher dimension.
In principle, yes, yeah. In principle, you can define entanglement entropy itself for any quantum field theory or any quantum system, but we are interested in renormalizable quantum field theory, usually. And in higher dimensions, quantum field theory becomes very trivial. Like in sixth dimension, it is like pi squared, so yeah, pi cubed. And also, as I have already told you, but, it can be a measure. So measure of degrees of freedom. Under the renormalization group flow. And I think Zoha will tell us about it. No? Okay. Okay, yeah, but yeah, in the second part of my talk, I will talk about the role of entanglement entropy under the renormalization group flow in quantum field theories, and I will explicitly construct some function, which I will call C function or entropic C function, by using the entanglement entropy. And the outline of my talk is as follows. So I will review the basics of entanglement entropy. Oh, yeah. Okay, so I'm going to review the basics of entanglement entropy first, and I move on to the first thing. And I will discuss the entanglement entropy in quantum field theory. So this is part 1. And in Friday, so I will talk about the entanglement entropy in renormalization group flow. And also, so recently I studied some supersymmetric extension of Renyi entropy. So Renyi entropy is a one-parameter generalization of entanglement entropy, and so I will discuss why we need to extend the definition of entanglement entropy or Renyi entropy in Friday. Sorry. Okay, so this is my plan. Okay, so let me briefly review what the entanglement entropy is. Okay, so to define entanglement entropy, so you need to divide your system, your Hilbert system, into 2 pieces. So here, so you have a time slice, so spatial slice of quantum field theory, and you divide your system into 2 regions, A and its complement B. And so I assume that the Hilbert space of the total system can be decomposed into the tensor product of the Hilbert space of A and Hilbert space of B. So this is very important assumption. And in this case, so we are supposed to have orthonormal basis for the Hilbert spaces. So for example, the Hilbert space of A has an orthonormal basis, phi 1, A, phi 2, A, So you have basis, and similarly for B's. And then we can define a reduced entity matrix.
Sorry, so this means that you ignore topological states.
No, you still have, I think, topological states.
They can also be factorized.
I think they can be factorized.
Okay.
Excuse me.
Yes.
Could you give us an example that a system is Hamiltonian cannot be factorized in this form?
Okay, for gauge theories, it's not clear how to decompose your Hilbert system into 2 parts. So once you put your system on lattice, then you have some shape for the region, and this is the boundary. So at the boundary, you would have some link variables of the gauge series. But so it's up to you. So whether this part is included inside A or inside B. But once you specify your decomposition, then you can clearly decompose your Hilbert system by extending the algebra over your system. But it's up to you. I think it's not so clear. So I don't think there is a unique prescription to decompose your Hilbert system in 2 pieces in the gauge series.
But could you give an example that a
okay, what I'm saying is that okay, there is a ambiguity in the decomposition. Yeah.
Take a quotient space.
Sorry? Oh, quotient.
Gauge some degree of freedom at that. It's a typical factor.
You mean engage degree freedom that you cannot take?
Yeah, the difference they can consider some quotients. You can consider some quotient of this factors.
I think realistically speaking, no Hilbert space can be factorized. The reason is that by acting with operators on Earth, you can create a less factor. It's a maximum factor that if you take some open set, or you study all the states in the Hilbert spaces, you can get the acting with operators from that set. You get something that's dense in the Hilbert space. So you can create something that's as close up to the as you want.
Okay, but okay, in this talk I will assume this decomposition. Anyway. Okay. So then you can introduce the reduced density matrix. So the definition of the reduced density matrix for the region A is that you take a trace over the Hilbert space B of the total density matrix. So this is the total density matrix. And the meaning of the trace is that you sandwich the total density matrix by the orthonormal basis by I, B. So these are the basis for the B. And you take a summation. So here I is the index for the basis. So I runs from 1 to the dimension of the Hilbert space B. So dB is the dimension of HB. So this is the definition. And also then entanglement entropy is nothing but the von Neumann entropy. So SA, entanglement entropy, is minus trace rho A log of rho A. Okay. So once you know the orthonormal basis for the Hilbert system, then you can compute the entanglement entropy immediately. And I will consider a ground state. So I will consider a ground state in the following. So in that case, the total density matrix can be written by using the ground state wave function psi, and I normalize the density matrix to be 1. So I divide it by the inner product of the normal ground state wave function. So this is ground state wave function. Okay. Okay, so I first consider a quantum system, quantum mechanical system. So which means that the dimension of the Hilbert space is finite. Okay. So since I assume that the Hilbert space can be decomposed into the tensor product of the Hilbert space A and Hilbert space B, so I can write my ground state wave function in this way. So I have a basis phi I for A and phi j for B, and I have some coefficients Cij, and I have summation for I and j. Okay, so this is a general state. Okay, if this coefficient Cij can be written as a product of Cia times Cjd, in this case, actually there is no entanglement entropy. That's because this state psi is just a product of some state psi A times psi B. So here psi A and psi B are new state. So this is Ci A times the original basis phi A. Okay, and similarly for B's. Okay, I changed the basis of the Hilbert space here. So where psi B is one of the bases, then it's clear that the resistivity matrix rho A is given by psi A and psi A. So this is a pure state. This is pure state. So there is no entanglement entropy. So SA is 0. So if you can write this coefficient in this way, then there is no entanglement entropy, because this state is just a pure tensor product, and there is no linear combination here. So this state is very special. So, but on the other hand, so when you cannot write Cij in this way, then there is an entanglement entropy. And so this is the general case. So in this case, so you can somehow diagonalize this coefficient Cij by using singular decomposition, singular value decomposition, singular value decomposition. So singular value decomposition means that Cij, oh, by the way, this matrix is not the square, but it is rectangular matrix, because the dimension of A and dimension B can be different. So this can be, this is just a rectangular matrix, Cij, and I think this is dA and this is dB, rectangular. And for any rectangular matrix, so you can, by using two unitary matrices, U and V, so this U, so this is my U and this is my V. U and V are unitary matrices. U and V are unitary. By using two unitary matrices, then you can diagonalize this matrix Cij, and whose entries are given by lambda k. So lambda k is positive, and k runs from 1 to the minimum of dimension A or dimension B. I mean here, so you diagonalize the rectangular matrix so as much as possible, and then the last term should be in my picture. So dA is less than dB. This is dB, and this is dA. Then you have dA eigenvalues here, and they are, as all of them are positive due to some theorem, mathematical theorem. And then, so you can rewrite your ground state vector in the Schmidt decomposition. So Schmidt decomposition is that the ground state vector phi is the linear combination of excuse me, phi tilde k for A and phi tilde k for B, and k in sum over k. And these are new bases. So you can, so by acting these two matrices to the original basis, you can redefine your basis. So phi tilde k are new basis, and you can rewrite this ground state vector in this way. So this is very simple picture. And here I normalize my vector. So the normal ground state is 1. This is my normalization. So it means that summation over lambda k squared is equal to 1. So then it is straightforward to compute the entanglement entropy because it is diagonalized. So the entropy is minus lambda k squared and log of lambda k squared. So this is the entanglement entropy for general state. And it is clear that because the role of A and B are symmetric in this picture, so A and B are symmetric. So the entanglement entropy for the region A is equal to that of the region B. Okay. And it's easy to see that the entanglement entropy is maximized. Entanglement entropy is maximized for so when all of the eigenvalues are equal, so when lambda k is equal to the square root of 1 over the minimum of dA dB for any k. In this case, entanglement entropy has maximum value. So the maximum value of entropy is log of this guy, so log of the minimum. So this is the maximum entanglement entropy. So this state is maximally entangled. Okay. So this is a very simple quantum mechanical example. And now, so I will list several properties of entanglement entropy, so which I will use in my later talks. By the way, can you see this? Maybe too small. Okay. Okay. Okay, so one of the very important properties of entanglement entropy is that strong subvertivity.